afternoon session, and I think we'll start off and let Hans take over after he comes. So, well, I think I'm going to temporarily chair until Hans comes. So we start with Sanchit Saraf and Sumit Saurabh. Sumit is the person giving a talk on characterization of successful formulas, the multi-agent case.
So if you have noticed, I've changed the title slightly. I've included the word towards because this characterization is not complete. It's a partial characterization, and this work is still a work in progress. But anyway, I'm happy to present this here and get some inputs on how to extend this. Okay, so let's start. This is a very simple example which you might already have seen in epistemic logic. So suppose there are two agents, Alice and Bob. There is a butterfly on Bob's head, which Alice can see, but Bob himself cannot. And then Alice makes an announcement to him saying that there is a butterfly on your head, but you don't know it. Now, before the announcement or before Alice says this to Bob, the model looks like this. So this is a very simple epistemic model representing the situation. There are two worlds, one in which the sentence P, which stands for there is a butterfly on your head, it's true, and the other one in which it's false. Now for Bob, these two worlds are indistinguishable because he cannot see the butterfly himself. But Alice can see the butterfly, so she can distinguish between these two worlds. Now, after the announcement, what happens is Bob knows that there is a butterfly on his head. Therefore, the not P world disappears for him, and he is only left with the P world. So these are the models before and after the announcement of this sentence P and not KBP. Now these kind of sentences are called Moorian sentences, and this is an example of an unsuccessful update. Now I haven't formally defined what an unsuccessful update is, but just to give you an idea, so if you look at this second model on the right hand side, the formula P and not KBP is false. So before the announcement, this formula is true, but after the announcement, the model gets updated and the formula becomes false. And well, this is an unsuccessful. So this is what unsuccessful means. The formula becomes false after the announcement. Before formally defining successful and so another thing about Moorian sentences is they're also related to this Ficht's paradox of knowability. So this sentence P and not KBP is an example of a sentence which can never be known. This is a true sentence, but you can never know this because what will happen is the formula will always delete the non-P words and the formula will be false after you announce it. Now this has been repeated a lot of times in this conference, so I'll not go over this in detail. This is the standard syntax of public announcement logic. Yeah? Yeah, so the agent to whom you're announcing this fact. Yeah, so that's the, okay. So this is the standard syntax of public announcement logic. We are in the multi-agent setting. So therefore we have an epistemic operator corresponding to each agent. Therefore we use ki, I is the subscript for the agent. Formulas are interpreted over standard Kripke models which are equivalent. So the relation Ri corresponding to each agent is an equivalence relation. The way you define the semantics of phi announced psi is as follows. So phi psi is true in a model if phi was true in the original model and after you announce it, psi should be true in the updated model. And the restriction, so the restriction is also defined in a very obvious way. You take away all the words where phi is not true, and relations and evaluations are also, so these are very standard things in public announcement logic. Now, so this is the formal definition. Successful formulas are those formulas which remain true after the announcement. So in the first slide that you saw, the Moorian sentence is an unsuccessful formula. It was false after it was announced. So equivalently, a formula phi is successful if it is valid in the model. So once you announce the formula, it should be valid. So box phi is valid in the model. Now, successful formulas have a lot of applications in epistemic logic. A lot of concrete epistemic situations can be analyzed by studying successful updates. And one very obvious observation that you can make is once you announce a formula which is successful, it becomes common knowledge. So if a formula is successful and if you announce it, it becomes known to all the agents that are there in your setting. A very natural question which people ask, therefore, is which formulas are successful? And by which formulas are successful, I mean you want to have a syntactic characterization of the formulas which are successful. Now, the problem with the syntactic characterization is that successful formulas lack closure properties. This was shown by Ditmarsh and Koi in their paper, that if phi and psi is successful, it's not necessary that their conjunction is successful. And we have already seen an example of this. So for the Moorian sentence, if P is true and not KP is true, if P and not KP are successful, their conjunction, which is the Moorian sentence, is unsuccessful. Similarly, phi may be successful, but not phi can be unsuccessful. And the same example is true, and so on. I mean, these are some examples which show why the characterization is difficult for successful formulas. There are some positive results. Now, for common knowledge formulas, you can say that they will be successful no matter what. Because for common knowledge formulas, no words will be deleted after they announced. So box C phi will always be valid, and therefore there will be common knowledge formulas. Another characterization, another partial characterization is by this theorem of Van Bendam and others, which says that a formula is preserved under some models if it is equivalent to a universal formula. And universal formulas are those formulas which are constructed using only literals, conjunction, disjunction, and the modality K. So for universal formulas, you know that they will be preserved under some models, and therefore they will be successful as a consequence. Now, for single agent case, Holiday and Icard, in their paper Moorian Phenomena and Epistemic Logic, they give a full characterization for the single agent case. So they say that the source of unsuccessfulness in case of a single agent is Moorian in nature. What this means is, for any unsuccessful formula in case of a single agent, it will have the form P and not KP. So they have notion of a normal form, and they transform any formula to this normal form, and they show that any formula which is unsuccessful has this Moorian nature, which means that there should be at least one binary operator in the formula. Now, the problem in multi-agent cases that formulas even with no binary operators can be unsuccessful. It's not a simple generalization of the simple agent case. So this is an example. We will see how this is unsuccessful later. Now, okay, so this is the problem, and we started by trying to see for which fragments of public announcement logic we can say whether it's successful or not. And we found that if you impose this restriction, so if you impose the restriction that any epistemic operator corresponding to an agent can occur at most once in a formula, then you can give a characterization. So we call those formulas simple formulas. So simple formulas are those formulas where the epistemic operator corresponding to an agent occurs at most once. And then you further classify. Well, this is just for the sake of giving a better classification, but we have the notion of a single term formula. Now, simple formulas which, so you have simple formulas where epistemic operators occur only once. Now you put a further condition that the binary logical operators do not occur outside the scope of an epistemic operator. So simply saying that the simple single terms are just single term formulas with this additional restriction of being simple. So they look like this. So E1 to En alpha, where E1 can be, so EI can be either Ki or Li, and by Li I mean just the dual of Ki, and alpha can be any propositional formula. So it cannot have any modalities, but just the logical connectives. Now, well, to make things even more simple, you can further classify them as K simple and L simple. And for K simple, you have only Ki as the epistemic operators, and for L simple, you only have Li. And it's very easy to see that for these K and L simple formulas, they will be successful. For K, it's very easy because you know that by this characterization of universal formulas, they will be successful. And for L simple also, you can argue that they will be successful using reflexivity of the frame. So if you have a bunch of L operators, and you're trying to show that the formula L1, L2, Ln P is successful, what you can get is a chain of related worlds. And since you know that the frame is reflexive, no worlds will be deleted after the announcement, and therefore the formula will remain true. If you think about it, the only way a formula can become unsuccessful is if one of the worlds in the model get deleted, and that leads to the formula being untrue. Now this is very simple, and then we notice that in case of multi-agent formulas, it doesn't matter. So the order of K and the L operators don't matter. The thing which matters is this. So the thing which matters is if you have a L operator in the scope of a K operator and vice versa. And for that we define KL simple single term. Now a KL simple single term is a formula where you have at least one L operator in the scope of a K operator. An example of this would be K1, L2, K3, where L2 is in the scope of K1. So this is a KL simple single term, whereas in L1, K2, K3, you don't have any L operators in the scope of a K operator, so it's not a simple single term formula. Now for this syntactic class, you can come up with a model which shows that, so let's take example of a very simple KL simple term, which is K1, L2, P. Now for this, you can, by this very simple model, you can actually show that after the announcement of this K1, L2, P, the word W3 will be deleted because there the formula is not true, and therefore it's unsuccessful. Now the interesting thing is that the same model works for any general KL simple single term. So what you do is, for any general KL simple single term, which looks like K1X L2P, you look at the first K operator, and you look at the first L operator, and you use the exact same model. So it's very nice in this way. I mean, you don't have to construct models for each of. So with this definition, you can capture all the formulas which have at least one L operator in the scope of a K operator. Similarly, for the other syntactic, for the other formulas, we have LK simple single term. So there, we put the restriction that it begins with all operators, and then you have no L operator in the scope of a K operator. So it's somehow dual to the KL simple single term. Now a very simple example is L1 K2P, where you don't have any L operators in the scope of a K operator. And you can actually reason that any LK simple single term will be of this form. So you will have a bunch of L operators followed by a bunch of K operators. And it turns out that they are actually successful. And again, so what you do is you start with a very simple example of such a formula, and the same kind of proof works even for any general LK simple single term. So this is also very simple reasoning. You start with a world and use the semantics of, standard semantics, and then since the frame is reflexive, it turns out that no world will be deleted and the formula will be successful, and the same idea works for this general LK simple single. And because of these three propositions, you can actually give a characterization for this fragment. So you can say that a simple single term formula is successful if and only if it's a KL or a LK simple single term formula. Now this was for very restricted fragment. So this is the fragment where you don't have any logical operators in the scope of an epistemic operator. What if you look at more complex formulas? So what if you look at multi-term formulas where you can have logical operators in the scope of an epistemic operator? So here, the AND that you have is not in scope of any epistemic operator, and for these kind of formulas, you have to reason by cases. So for example, if you know that phi and psi are unsuccessful, you can show that their conjunction is also unsuccessful. And again, the idea is not very difficult. What you do is, since you know that they're unsuccessful, you use each of their counter models to construct the combined counter model, and you let them have a common world, and that actually works. The thing is that since they don't share any epistemic operators, as they are simple formulas, we don't run into any problems. Similarly, if phi is successful and if psi is unsuccessful, their conjunction is also unsuccessful. Again, you use the counter model, and so this is the idea of a proof. I'm not going into the details because I don't have so much time. So, and what happens is if you have, well, so for the conjunctions of successful formulas, if phi and psi both are successful, then the analysis is more complicated. So you have to look at different cases, and well, this is a summary of different kinds of results. One thing to notice here is the formulas which are unsuccessful usually have a k operator in the scope of a L operator. So if you see number 4 or number 3, for instance, so there the reason for unsuccessfulness is a k operator being in the scope of an L operator and so on. But again, I mean, you have to look at different cases and do this case by case characterization. Now the ideas are not very complicated, and the reason is that we have restricted this class. I mean, you allow for only one occurrence of an epistemic operator. So the things become more complicated when you have more than one occurrence of an epistemic operator. So this is just to give you an idea why things become complicated in the compound formulas case, where we can allow for more than one occurrence. I think I'll skip this. So I mean, just to give you an example. So in the compound case, K1L2 K1 alpha, which would have been classified as a KL formula, here becomes successful. And one of the reasons is the frame is transitive. So occurrence of an epistemic operator more than once creates this problem, and the generalization doesn't transfer to the compound formula case. Now this is my last slide, and yeah. So well, since this is a work in progress, I have a lot of directions that I want to explore. Now, Moorian phenomena, which was for the single agent case, says that even for weaker logics, so for the logics of belief, KD45, there as well the Moorian phenomena is the reason for unsuccessfulness of a formula. Now, we saw that most of the proofs in the multi-agent case rely on the frame being reflexive and transitive and so on. So what happens if we drop some of these conditions? It will be interesting to see which formulas remain successful or not. And it will also be helpful to find a normal form along the lines of that paper, which helps us to classify compound formulas. And another one very last point that I want to mention is there is this notion of epistemic algebra. So because of the duality between frames and algebras, you can see public announcements also as, so you can see as announcements on the algebraic side as well. And here you say that a formula is successful if it is true in the submodel or the subframe. And on the algebraic side, what happens is you can have an equivalent notion of success and say that a formula is true or successful if it is true in the quotient algebra. So it will be interesting to see which equations are preserved under quotient algebras to give a characterization. Thanks. Can you work in the normal form for PAL itself? Well, normal form approach is a bit different because there they have this so they start with a standard normal form, and since they want to show that the source of unsuccessfulness is Moorian, they want to transform the formula to this normal form. So I think it doesn't really depend on which logic you are in. I mean, that's a standard. So the normal form there is from modal logic, as in it doesn't depend on the logic you're in. Yeah.
In the multi-agent setting, I think you could try the disjunctive form, which would be the multi-agent equivalent here as well, and you could rephrase this in cover modalities and see if it makes that easier.
Yeah, I haven't really explored all this. I mean, this is still, like, I would like to see. Yeah?
Yeah, I have a very simple question. So, if at the beginning of your talk you gave Van Bintum's result on like a formula is equivalent to universal formula even only if it's preserved under restriction. Why doesn't that give the full story?
Because it's a very restricted. So if you see the result, it says that, well, so I mean here you don't even have any L operators. I mean, so
how do you mean an L operator?
And a universal formula is a very, very restricted fragment. It only has k conjunction and disjunction. So
No. I think there's a misunderstanding here. What Van Bentham means, the translation into first order logic has to be universal. And you have a much more restricted class. You will see that in lots of, I think in all of your examples, it will turn out, if you translate them into first order logic, under the appropriate restrictions for the model class, and then do some first order calculation, then you will find out that it will be universal formula. Otherwise, you would have a counterexample to Van Bentham's theorem.
Maybe we can leave it with this very interesting observation, and despite the interest to the audience,
we'll talk about it.
Continue. Yeah, thank you.
okay.
Okay, the next presentation is by Pavel Naumov on the shield wall principle.
So this is talk on concurrency, and the standard example in which people introduce knowledge of concurrency seems to be Dijkster's Dying Philosophers. So here we have 6 philosophers sitting around the table. They chat and eat. Each philosopher has its own plate, but there are forks placed between philosophers. In order to eat, philosopher needs both forks, but he can pick one of them at a time, wait for the other to become available, and start eating. That normally goes very well, except that it might happen that all 6 of them pick, say, right fork, and the situation comes to deadlock. If they are stubborn enough to follow the rules, they will eventually die from starvation. Now, this system has 2 deadlocks, one when each philosopher picks the right fork, and another when each of them picks the left fork. I'm interested in the notion of interference, and I would say that it's pretty clear that Plato here interferes with Russell, because if Plato only lets Russell have his fork, Russell will be able to eat and survive. Now, what might be a little bit less obvious is that, at least in my view, Kant is also interfering with Russell. They have no common resources to share. However, if we remove Russell from the table, then this fork becomes available, and Plato can eat and release the fork, and eventually Russell will be able to eat. So Russell clearly is waiting for Kant, and I will say that Kant is interfering with Russell's desire to eat. We will study this interference, or indirect interference, relation, but it's much easier to talk in terms of negation of interference, or non-interference, or as I like to say, independence. So if removal of Kant would not allow Russell to eat, there is no way, no chance for Russell will be able to continue, then I will say that Kant has nothing to do with Russell, and therefore Russell is independent from Kant. In our case, however, it's not true. Russell is not independent. Right? Okay. Each time when I will talk about concurrent system, I will associate a hypergraph of resources of such system. This is a hypergraph where each H represents a process, in our case, philosopher, and each vertex represents a placeholder where we'll store resources, one or maybe several resources. Hypergraph is trying to capture topological structure of concurrent system. Who has access to what and how we interfere. Clearly, for the same hypergraph, you can come up with different concurrent systems, but will have different properties. Just to entertain you a little bit, I will talk about a variation of dining philosophers that I call two-headed dining dragons. So we have a table again with 6 plates and 6 chairs, but we place two-headed dining dragons with chairs. Each head needs a fork and a knife in order to eat, and so we'll place those between. But let's assume that dragons treat their heads in extremely equal fashion. If one head grabs a fork, the other head must grab the fork at the same time. If one head starts eating, the other head must start eating. So we're synchronous processes, and we must do things at the same time. If this is the case, then it's easy to see that system here has, again, two deadlocks. One possible deadlock when each odd-numbered process has two forks. Odd-numbered dragon has two forks. And another deadlock, okay, and the other have two knives, and the other deadlock is when it's the other way around. So far, situation is very similar to dynamic philosophers, right? You have 6 processes in a circular hypergraph. You have resources, and you have 2 distinctive deadlocks. Now let's talk about interference or independence for those 2 processes on the same hypergraph. First of all, if I remove P1 and P5 from the table, then clearly P6 will be able to finish, because there's nothing, we will release the forks, and P6 now will have all it needs to finish. The same actually is true for dragons. If dragons P1 and P5 both release the resources, then P6 will have 2 forks, 2 knives, should be able to finish eating. Now, if I only remove P1, then in case of dynamic philosophers, what might happen? P1 might be holding the left fork over right fork. If it's a right fork, then P6 will immediately grab it and finish eating. If it's left fork, then as I have shown on the first slide, will be just this wave of eating going around, and eventually P6 also will be able to eat. So if P1 releases its resources, then P6 will make a move in case of dynamic philosophers. In case of dynamic dragons, no. If you remember our deadlocks, well, in deadlock P1 holds 2 of the same type of tools, 2 forks or 2 knives. Let's suppose it holds 2 forks. Then P3 is holding 2 forks and P5 is holding 2 forks. If P1 releases those 2 forks, neither P2 nor P6 will be able to make a move because they need the second fork. So in this case, when P1 releases resources, P6 will not move. And I will say that P6 is independent from P1. In fact, for dragons, much stronger claim is true. If all P2, P3, P4, all of them release their resources, P6 still will not be able to move. And this is very different from philosophers. While being logician, I'm interested in general universal properties. In this case, in the universal properties of interference, which are true for all concurrent systems. Not properties specific to dynamic philosophy or dynamic dragons, but properties which are true for any system for a given hypergraph of resources. So I would say those are properties of the hypergraph of resources, right? So what kind of properties do we have here? Well, here's an example. If P2 and P4, when they release resources, P6 doesn't move, then when P3 releases resources, P6 will not move either. Why this is true? Well, you can kind of imagine a wall formed by P2 and P4. Releasing resources in P3 is not as powerful as releasing everything P2 and P4 have. When you release everything that P2 and P4 have, you do as good for left-hand side as possible, right? You provide them with maximum amount of resources. And so this is why it's true. This property, this thing I will sometimes call gateway, and so this is gateway property, could be generalized for arbitrary hypergraph. If you have 3 sets, A, W, B, where W is a gateway. Gateway means every path from A to B goes through W. Then if A is independent from W, then A is independent from B. Well, OK, so we have something. But it's not really interesting. It's something that you would expect. Right? All interference happens locally. There is no secret tunnels in the space space worms. If you interfere with me, then it should come through the path that leads towards me. So something like this is quite expected property. More interesting question is there something else? And the answer is yes. And here's another property. There's no gateway here. There's no way we say I'm independent from this block. This block cannot move. So what we kind of have two different chunks of gateway, one over here and now over here. And the formula is true if you analyze carefully what happens here. But what I want to do is to think about this formula and this hypergraph as a setting where P1 and P5 are two medieval knights guarding left-hand side of a graph. And P2 and P4 are their shields. So they're guarding left-hand side of the graph from the enemy on the right. None of them actually completely blocks left side from the right side, but together they do. This idea is quite old. I would say it goes to, again, to some ancient times when people would use shield walls as a military tactic, right? Warriors will surround themselves by shields. None of the shields completely blocks warrior from enemies, but when they stay together, say in a circle, this group of warriors is blocked, completely protected by the shields. We can extend this analogy, and it turns out that the following property is true. If you have warriors, A1, A2, A3, A4, well, in reality, those are processes. Those are edges of the hypergraph. And we have shields, S1, S2, S3, S4. Those, again, are sets of edges. We have enemy, B, again, set of edges in the hypergraph or set of processes. Then if each of warriors cannot be disturbed by its shield, then all warriors taken together cannot be disturbed by the enemy. Just like it happens with real shields. Now, at this point, you can say, OK, good. This guy should just read more military textbook and learn some other military tactics. Maybe something more modern. Well, it turns out, no, I don't have to, because there's nothing more to this relation than this shield wall principle. If you pick two trivial axioms, empty set and monotonicity, and add the shield wall axiom, then a system is sound and complete with respect to the semantics I kind of sketched out before. Yes?
What is in the shield wall axiom, what is the relation of B to the shield spectrum?
OK. So B should be outside. It means that any path from a warrior to B must either go through shield or through other agent or other warrior. OK, so this is it. Now, we talked about gateway before, right? And gateway, of course, is just a trivial case of a more general shield wall principle. Here, A is just one warrior, and it has one shield, W, and you get exactly what you need. Now, it turns out that on the same picture, you can make another claim. You can say that if gateway is protected against enemy, then anything inside gateway is also protected. This is different from what we had as a gateway principle. And in fact, as far as I know, it does not follow from gateway principle. Gateway principle said if W cannot disturb A, then B cannot. And so this is different. But this does follow from shield wall. Indeed, we pick A to be our first knight, warrior. W the gateway, is the second warrior. The shield of the first warrior is empty. Shield of the second warrior is the enemy. Well, magically, if you write down shield wall axiom, and when this is always true by the empty set axiom. Empty set cannot disturb anything. So when the difference between what we have right now and what we need is just this extra W, but could be removed by monotonicity axiom. And we're done. Here's another example to illustrate how shield wall could be used to reason about interference. I picked this specific example because it shows that shields can overlap. Shields of physical warriors are distinctive, right? They don't melt together or anything like this. Shields in this axiomatization can overlap. So what we pick here as A1 is one warrior B. A is one warrior, B is another, C is the third, and D is the fourth. This is more or less what we have over here. But shields now, shield for the first guy is empty set. Shield for the second is F and C. Shield for the third is F and H. And here shield is C and H. So they pairwise, not disjoint. Well, if we just write down shield wall axiom, we get this. And again, by empty set, this is false. Oh, this is always true by empty set axiom. So we can get rid of it. Now, difference between what we have and what we want to get is just that we have single A over here and multiple guys over here. We can get into them by by monotonicity. My time is running out. This is my last example. And it shows that shield doesn't have to be directly attached to the warrior. It could be several miles away. So to prove this formula, those are our warriors. A3 is a set, so it's E and H together. And their shields are B, which is far away from A. And this is shield for C. And this is shield for this warrior. Again, they quite far. They are not adjacent edges. And simultaneously, this is also the enemy. If we write down now shield wall axiom and apply monotonicity, we'll get what we want. OK. Now, it turns out that exactly the same axioms appear in a very different setting, in information flow setting. And if you consider what we called belief propagation network, where some false beliefs spread around multi-agent system, then the laws of propagation of those false beliefs are exactly the same as laws of this, non-interference and concurrency. And this is a paper which I presented in September in Toulouse.
I have a question, actually. Could you point out the difference between the JVM work that you presented there and the continuation of your ideas here? I didn't get that.
So this is about concurrency.
Yeah.
The other work was about information flow. So it's the same axioms that appear in spreading information between agents.
OK, but it had the shield wall principle.
It had exactly the same axioms, right?
OK, yeah. And are you thinking of different applications here because of the concurrency relation? Or?
No, it's again my attempt to show that the world is universal. The same principles appear on both sides. I think here is actually a more natural setting than in information flow. But.
OK, thank you very much. OK, the last speaker is Hitoshi Omori and Michael Day. And they on expansions of FDE and classical negation. So these are all 20-minute presentations, and after that we have a break again, which will be 5 minutes shorter than announced.
Okay.
I would just like to say thanks for having us at this conference, which is in such a spectacular place to give a talk. So actually, it turns out that me and the co-author are actually here together, which is unusual. So we're both going to try and present this together. I'm just going to do the first half, which is philosophical, and the co-author will do the second half, which is going to be more formal. Okay, so we're going to talk about expanding FDE with classical negation. And FDE is a kind of logic which allows for gaps and gluts, which we'll come to in a moment. So I'll just skip the abstract. So you might wonder why. So FDE is a kind of pair-consistent logic, and you might wonder why you want to add classical negation to a pair-consistent logic, since classical negation is not pair-consistent. But there's been some interest in the literature, and some initial interest has been by Meyer and Routley, where they discuss adding classical negation to the relevant system R. So here are two fallacies of relevance that classical negation gives rise to. So the first one is just that if A, then B, then A, and if A, then not A, then B. Well, in the first case, it's classical implication. In the second case, it's because of classical negation. Now, what Routley and Meyer do in a series of papers in 73 and 74 is consider adding this negation here. So if you take the frame semantics for relevant logic, which is just a crypt key structure, and then you have a ternary accessibility relation, and then you define a partial order on that crypt key structure, which preserves truth up that partial order. Then what happens if you try and add a negation like this, which just looks like classical negation in the crypt key semantics setting? So you say that not A is true at a point A in a model M, if and only if A is not true at the point A in the model M. Can you add this and not get untoward consequences? So if you tried to do this in the crypt key semantics for intuitionistic logic, it wouldn't work because it would break the preservation or heredity condition, which says that if a formula is true at a point, then with respect to this partial ordering, the formula has to be true at every successor point. Well, it turns out it breaks in this case too, but what you can do is just consider the models in which the partial order is just the identity relation. And then you get classical negation, and you conservatively extend the logic, which is an interesting result in this case. So anyway, the upshot is that you can add classical negation to the relevant logic R. And there's no untoward consequences. It's conservative. It doesn't collapse into classical logic. So all is good there. So one question that Hitoshi and I had, we're just wondering whether we could add classical negation to other pair-consistent logics, and one in particular is the context of FDE. So we show a sort of similar thing, which is that you can add classical negation to FDE in it, and you don't run into these untoward consequences. Okay, so here are just a couple of reasons why you might be interested from a pair-consistent perspective in classical negation. So the first one is just what I just mentioned, to show that adding classical negation to non-classical systems doesn't yield undesirable results, namely a collapse into classical logic, for example, or getting non-conservativity, so you get formulas in the base language that you didn't want when you add classical negation.
When you say doesn't,
yeah. When I say it doesn't, I mean
it never does?
It never does. Yeah. And the second is because the negations of non-classical logic, such as relevant logic, they've been criticized for not being genuine, right? So a lot of people think that the negation of, yeah?
What about many-value logics? If you add classical negation, you end up doing nothing.
It depends. So if you take the three-element, so take the gappy logic of Kleene, K3, then you can't get a Boolean algebra. But sometimes. But it depends what's meant by classical negation, and we'll discuss that in a second. Yeah, good. So one is that classical negation in these contexts is Boolean complementation, but it might not be. Okay, so if you think that, say, a pair-consistent negation is not really genuine, then to appease the objector, you might say, hey, we can still add classical negation to the system, and that's okay too. So this should satisfy you as well. Another interest that comes up in the truth literature a lot is this notion of classical recapture. So you want to get as much of classical logic as possible. Well, in this context, if you have classical negation and you have classical disjunction or conjunction, then you have all of classical logic anyway. So that's as close to classical recapture as you're going to get. And another is that you can view classical logic as a fragment of certain non-classical systems by adding classical negation to the latter. So you have an extended language that has classical negation in it, but it also has some non-classical connectives in it as well. Okay, so what is classical negation, which comes back to this point here? Well, in the context of FDE, there's various ways you might define classical negation. So this is the standard diamond algebra for FDE, where on the right-hand side of the slash, it's just names for the truth values. So you have false at the bottom, truth at the top. On the left, neither true nor false. And then on the right-hand side, both true and false. And then on the left-hand side of the slash, it's just if you took the truth values to be elements of the power set of 2, where the inclusion ordering goes from left to right instead of bottom up. Okay, so a more general question is kind of what is negation in general in the context of pair-consistent systems? Now this is a famous objection by Hartley-Slater, and here's a verb which is to Slater an operation, or to Slater a negation in particular. It's to deny that this operation is a negation if it's not semantically contradictory forming. Namely, it doesn't satisfy the two following clauses. So it's not either it's not a contrary forming operation, so A and not A cannot be true together. That means it's a contrary forming operation. And it's subcontrary if A and not A cannot be false together. So if you have an operation and it fails to satisfy one of those two conditions, then you might not think that it's a negation. And that's essentially what Hartley-Slater's objection is against some pair-consistent negations, including Grand Priest's negation of LP. Because you can have sentences being both true and false. So it fails to satisfy contrariety. A and not A can both be true. So then you might not think it's a negation. And call this the sort of traditional formulation of contradictoriness. Okay, so if a negation is just a contradictory forming operation, then various pair-consistent negations won't be negations according to this, because they won't be contradictory forming. Okay. This is what essentially Priest says to respond to this objection by Slater. He says, well, forget about the classical formulation. Consider this one. It's actually logically, it's classically equivalent to this formulation. So define contrariety in this way. One of A and not A is false whenever the other is not false. Right? So if one is false, not false, sorry, then the other is false. And subcontrariety is one of A and not A is true whenever the other is not true. Okay, equivalently, it can be stated in this way. Well, if you think of the negation of LP, so you have a 3-element algebra on the bottom, you have truth, then you have both true and false, and then you have true only at the top. And a sentence can be both true and false. Then the negation actually satisfies this, the both true and false. Because when so the only degenerate case is when the sentence is both true and false. And if it's both true and false, then whenever the other is not false, the negation will be false. Right? So it satisfies contrariety this time, whereas before it didn't on the traditional conception. Okay, that's good. But actually, this only satisfies only one negation. The negation of LP satisfies these two conditions. And you might want to hope that the negation of FDE and other pair-consistent logics will be contradictory forming, but they won't be according to this one. So these distinctions between these different definitions of contradictoriness are subtle because they're equivalent classically, but they come apart in the non-classical setting. So here's one final further definition that's classically equivalent to the initial one, but actually comes apart again in a non-classical setting. So take contrariety to be one of A and not A is false whenever the other is true instead of not false, which was Priest. And subcontrariety is one if A and not A is true whenever the other is false. If you think about it for a second, you'll see also that the negation of LP is going to be, we'll call this the Amori D formulation of contradictoriness. And the negation of LP, K3, both types of negation, one's called LP, one's called exclusion, one's called choice. Choice is a fixed point on the gappy value. And flips true and false. And the negation of FDE and a host of other non-classical logics turn out to be contradictory forming on this definition. This is good if you think negation is just a contradictory forming operation. Actually, what's more interesting about this definition as well is that it serves as a non-circular definition of negation because not is not occurring in the definition itself, whereas not occurs in the definition of contrariety and subcontrariety here, and likewise for the traditional formulation in cannot. Okay, so this is a more legitimate definition of negation as contradictory forming operation. I'm now halfway? Okay, thanks. Okay, so, right, so this was just a digression into what is negation in this context. And what we're going to consider to be classical negation in the context of FDE is just Boolean complementation, in this case in the diamond algebra. So it can be characterized this way, and it just has this truth table, which is familiar, right? It flip-flops T and F and flips B and N. Okay. I won't really talk about this because I don't have time, and I'll let Hitoshi quickly take over for me now.
So Mike provided this formulation in terms of many-valued or traditional way. But we can see the FDE things in a different perspective. That is the relational semantics. So we usually interpret formulas through functions, but we can also do that not by functions, but relations now. And if you see the semantics of FDE in terms of this relational semantics, it goes like this. So for the truth and, for the negation and conjunction destruction, these are the primitive connectives. And we always have to provide the truth conditions as well as the falsity conditions, because here the truth and falsity are not necessarily related. And so, and in view of this, we can compare the exclusion negation and the classical negation we just set out. And we call the independence, we call this truth and falsity should be handled on a par as an independence criterion. And to advocate this, we need another different discussion for this, but we will just assume this one. And then the exclusion negation looks like this. Namely, it's true if it's not related to true. So the exclusion negation of A is true if A is not true. And the exclusion negation of A is false if A is true, okay? So in that sense, truth and falsity are in a sense not handled on a par, whereas the classical negation we set out, well, namely this is a Boolean negation, satisfies the criterion of independence, namely for both cases, it realizes the reading of not in the kind of meta language. And we can also compare the difference between the FDE negation and the classical negation. And for this purpose, I just wrote 2 diagrams. And what FDE negation does in this context is to relate the truth and false. So it relates the 2 circles, okay, in the FDE case. Whereas what classical negation does is to show if it's in the circle or not, okay? So we have 2 circles, so we have 2 conditions for that, okay? And if we think of the classical setting, then the truth and falsity are exhaustive, and exclusive, okay? So it looks like that. And in this case, those 2 negations are the same thing. Namely, if it's related between true and false, it's also doing if it's in that area or not. So in this way, we can clarify what, in a sense, we can distinguish 2 aspects of the negation in the classical logic. And so we turn to the more of a proof theory. And we can axiomatize the system having these 2 negations. But for the purpose of, for the sake of the presentation, we add the conditional connective 2. And for the negationless fragment, it's just like the classical logic. And for the negation-related fragment, the first 2 axioms, the 10 and 11, are exactly the one for the classical negation. And 12, 13, and 14 are for the kind of familiar FDE axiom. And since we have both of these, the Morgan negation, FD negation and classical negation, we have to set how they are interrelated. And those are stated by 15. And 16 clarifies how the conditional behaves. And as for that system, we have the deduction theorem, since modus ponens is the only rule of an inference. And we can also prove that this system is complete with respect to the semantics we've been talking about. Note that the semantic consequence relation is defined as the preservation of designated values, namely T and B, in the four-valued way of presentation. And furthermore, we can prove also that, so FD is simply obtained by adding this classical or Boolean negation to FDE. And we can prove that that exclusion negation cannot be defined within FD+. And we can also say the other way around, namely, if we enrich this FDE by this exclusion negation, then you won't be able to define this Boolean negation. And as a corollary, you can say that this FD+ is not functionally complete. And also, well, so we can just say this result in a word, in a sentence, because there won't be any Boolean algebra with 3 elements. But speaking of that in a different way, we can say that the classical negation or the Boolean negation cannot be realized in the 3-valued setting. So the classical negation we specified is specific to 4-valued, not possible in a 3-valued case. That's it. Thanks.
So by classical negation, you were trying to mean that only those two properties mentioned earlier means
this one?
No. Okay, I remember. Those two properties means A and not A false together. They cannot be true together, and contrary or some sub-contrary, I think.
You want to see that one? This one. This is the one for the classical negation in our sense. Huh? Oh, that one. This one?
Yeah.
Okay. This is not the classical negation. This characterizes the FD negation or the so-called De Morgan negations.
So what is this another negation, exclusion negation? I saw some.
Exclusion negation?
In your last slide, I think.
This one?
Yeah. Oh, no.
I don't see that one.
So, no, not that much.
This one? Yeah. Okay.
Yeah. So
usually the upper part of the conditions are thought to be characterized in classical negation, right? And indeed, if you think of those, so in case of FDE, there are kind of 16 candidates satisfying this condition, 16 unary operations satisfying this condition. And that will be sufficient to characterize proof theoretically the classical axioms, namely the law of excluded middle and explosion law. So the problem arises in the related to the De Morgan negation part, namely the falsity part.
Means from these two definitions, these are syntactically seeming quite similar. So I do not get where is the difference actually. Means.
Yeah. So if you have the upper clause, right? Mm-hmm. And if you restrict your attention to the positive connective together with this negation, then it's going to be totally the same. Okay.
Okay.
The difference occurs in the relation between the De Morgan negation, tilde negation, and this classical negation, and that's going to be characterized in a different way.
Okay.
Depending, yeah.
Thank you.
Thank you.
Other questions? How did you prove the
completeness? What is the procedure?
Oh, you can prove it by the Kalmar's constructive procedure.
Kalmar's.
Yeah, or whatever you want to, but you can do it in the usual way. Thank you.